Okay, continuing with what we were covering last time, primarily the clustering, rather the core, at the core of clustering, the major player which can influence the results of the clustering is the distance measure, or we call it the similarity measure. People call it dissimilarity measure, similarity measure, distance function. So this is at the core of any clustering algorithm. And the quality of the clusters, which we discussed last time, is primarily dictated by the distance function as well. There are other factors as well, for example, type of the data, category of the data, problem domain as well, and noise in the data. But the major thing which influences the quality of clusters is the choice of the distance function which we make for the clustering process. So last time I was talking about the different requirements and expectations which we have from the clustering algorithms, but today our focus will be more on the distance measure and the data type of the data which we have. So usually we have two types of data. Either it is a data matrix or it's a dissimilarity matrix, right? So the data matrix is also called a two mode matrix, right? For example, I have I have record number 1, I have record number 2, I have record number 3 and record number 4. Similarly, for all these records, we will be having variable, or let's say attribute 1, attribute 2, attribute 3, attribute 4, attribute 5, where this attribute 1 can be maybe name, attribute 2 can be, let's say, age, attribute 3 can be sugar level, attribute 4 can can be congestion in chest, and so on and so forth. So if you see here, this is a data matrix which is two mode. The rows represents different entity and the columns represents different entity. So these are two modes, right? So the data which we have can be a data matrix which we are given for for clustering. This can be two mode, as you can see here, and it can also be a dissimilarity matrix, where the dissimilarity matrix is always one mode, right? Okay, and how does that dissimilarity matrix look like? Let me try to demonstrate it. For example, I have record number 1 and I have, let's say, record number 2, and let's say I have record number 3, and all these records records have attributes. For example, this has attribute number 1, all of them has attribute number 2, and let's say all of them has attribute number 4. Okay, let me make another. We have attribute number 4 as well for all these records, right? Now, what will we do to find the dissimilarity matrix? We will make a matrix like this. Okay, the first row or first cell of the matrix will be like this: R1, R2, and like R3, and these are the rows, and the columns will be like again R1, R2, R3. So it will be a 2D matrix. Now what will we do? I've made a big matrix, so okay, right, so we can ignore this portion of the matrix, right? So it's a 2 by 2 matrix. Now here, what will we do? We will pick this record, right, and we will be having a distance function, right? And this we will be giving r1 and this r1 again to this distance function, and this distance function will give us a distance value. It will be a numeric value, and that numeric value will be placed here. If you see here, we have given this distance function two records, both are same, so distance between them is most probably going to be 0, right? Now for the next cell, what will we do? We will give it r1 and then we will give it r2, like this record. And now these are two different records which will be going to this distance function, and this distance function will be computing similarity or dissimilarity between these two records, and it will be giving us a numeric value, and that numeric value we will be placing here. For example, it's like say 7.6 for example. Again, then moving on to the next cell of this dissimilarity matrix, we will be giving it record number 1 and we will be giving it record number 3, and it will give us the distance between them. How will be it computing this distance value or distance measure? That is a different thing. I'll be covering those formulas shortly, but what I want to explain here is that this is a one mode matrix, right? A one mode matrix where on the x-axis and y-axis we only have records, and each cell of the matrix represents the distance between the entities r1, r1, r2, r1, r3, r1, right? And this is called a one mode matrix or dissimilarity matrix. And as you can see that it is always symmetric, right? This matrix is always symmetric. For example, this cell may represent record 1, this cell may represent record 1, and this cell may represent record 2, and this cell will represent record number 2. So whatever value is here will also be here as well. So we can simply ignore the half of the matrix, because we know that the distance between r1 and r2 will be equal to the distance between r2 and r1. It's simply like the distance between Islamabad and for example Topi, and the distance between Topi and Islamabad, both are the same, right? So it means that the half of the matrix that can be ignored, and you know that while reading this matrix we will be requiring two loops, so we can write a program a bit efficient so that we can ignore a lot of values, reading a lot of values which are basically redundant. So these are the two data structures or the data which we will be dealing with while we get the data from the after the pre-processing and stuff for the clustering procedure, right? So either we have the data matrix which is 2 mode, or we have the dissimilarity matrix which is 1 mode, right? Then the okay, let me read out the slides so that I may not miss anything. Dissimilarity or similarity matrix is expressed in terms of a distance function, which is typically a metric. There is a separate quality function that measures the goodness of a cluster. Okay, this should have been covered here while I was talking about the quality of the cluster, but okay, let me discuss that. Once we have attained the or achieved the results of clustering, there are certain measures which measures the quality of the resultant clusters. For example, there is a coefficient called as Silhouette coefficient, right? So we can measure, and the Silhouette coefficient has a value between 0 and 1. For instance, if you have done your clustering, what you do, the resultant cluster, how will we doing clustering, I'll be discussing in the coming lectures various algorithms to cluster the data, but let's assume that we have clustered the data and we have got the results, that okay, first 6 records are in cluster number 1, 5 records are in cluster number 2, and 8 records are in cluster number, let's say, 3. So what we will be doing, we will be computing for these clusters, we will be computing the Silhouette coefficient value, and okay, let me, for example, let me demonstrate it. For example, this is a clustering, right? This is a clustering which we have done. Certain items are like, we have total, let's assume we have total 9 objects in the data, right? So if you see here, some are blue, some are green, and some are red, but this is, let's say, clustering number A, right? And then we have another clustering for the same data. We cluster the data, for example, like this somehow, and okay, and okay, now this, if you see here, since the same data, but the formation is a bit different here. In this clustering formation, let me call it B. So for the same data, we have clustering formation A and the clustering formation B for the same data, right? So what will we be doing? We will be giving both of these clustering, rather we will computing the SC, Silhouette coefficient value, for clustering A, and let's assume the Silhouette coefficient value for clustering A turns out to be, let's say, 0.9, right? And the Silhouette coefficient value for clustering B turns out to be 0.6, right? So for Silhouette coefficient value, if the higher the value of the Silhouette coefficient value, better will be the formation of the clustering. So if you see here, assuming that this value is obtained for the clustering formation A, it means as compared to the clustering formation B, clustering formation A is better, right? Now one question can turn up in your mind, that why are we getting multiple clustering formations, right? We can get a whole ton of clustering formations for the same data, because we are dealing with unsupervised learning problem. We do not have the ground truth, so that is why we don't have the exact answer which we want to obtain. That is the reason we are relying on the quality matrices to compute or gauge the quality of our results. So coming back to what I was saying about the dissimilarity or similarity matrices, the definition of the distance functions are usually very different for interval based, Boolean, categorical, ordinal, and ratio values, because in your data certain values may be of let's say integer type, certain values may be Boolean, certain values may be let's say true and false, and categorical values may be colors. Colors have categories, they don't have continuous values. So computing distance for such values is a bit challenging. For example, if you want to cluster the data of players, for the basketball players, then there certain variables are very important. For example, the height is a factor which is very important factor to be considered while selecting or dropping a basketball player. You need to have tall players for the basketball, right? So for example, maybe in the domain of medical informatics, maybe age may be an important factor, right? But what I want to emphasize is that for a record, we can have a variable 1 which is of type int, right? We can have a variable 2 which is of type bool, right? And okay, and we can have a variable 3 which is of a type uh, which is categorical. So we need to know to how to compute distance for each and every type of the variable, right? So the types can be, the usual types can be interval scaled variables, binary variables, nominal or ordinal ratio variables, and mixed type variables, right? So one thing usually which is done in pre-processing the data is to compute the standard deviation of the data. Or what we can do is we can compute the standard deviation, or we can compute the z-scores, right? So generally the use of absolute deviation is more robust than the standard deviation, for obvious reasons, because absolute deviation is more representative of the pattern in the data as compared to the standard deviation, right? Then this is the instead of focusing on this is the primary thing which needs to be focused, right? So there are a lot of similarity measures. We can call it similarity or dissimilarity, both are the same in terms of notation, in terms of nomenclature. Now, this is the general form of the distance function. For example, if we have a record, for example, there is a record of person 1, and the value of his first attribute is, let's say, 3, the value of his second attribute is his or her whatever is 5.5, the third attribute has value 9.5, and the fourth attribute has value 0 or 1, okay? And we have record, okay, blue, we have another record 2, and the first attribute has value 2, the second has 5.5, the third has 9.1, and the fourth one is 0, right? So this thing is record number 1, and this thing is record number 2. Now what will we do? We will pick first attribute from here. We will be picking first attribute from here, putting it here, right? We will be picking second attribute from here, second attribute from here, and putting it here, and putting it into the formula. We will be obtaining the value. So this is a general form of which is known as Minkowski distance. But in the Minkowski distance, when we put the value of q equal to 1, we get this formula, and this is called Manhattan distance, right? So the records which I placed showed to you earlier will be simply putting their values in this equation, and we will be getting a distance value, right? So this is the Manhattan distance. We have other distances as well. For example, Euclidean distance. If you see the shape of the distance, the Euclidean distance is almost similar to Manhattan distance, but we have an added value which is the square root value, right? So both can be used, but remember, for a data, for example, okay, let me, for example, okay, wait, R1, R2, R3, right? For example, if you compute the distance between R1 and R2 and you use Euclidean distance, and maybe for the distance between R2 and R3 you go for, let's say, Manhattan distance, so that will be wrong, right? So throughout, if you choose one distance measure, you have to use the same formula throughout your clustering procedure, right? So making the choice of the distance measure is a it's a prereq to executing the complete clustering process. You cannot switch between various formulas or distance measure during the execution of the clustering, right? So you have to stick to one. Then but these are general formulas. Manhattan distance, Euclidean distance, Minkowski is the generic form. Manhattan and Euclidean are subtypes of those, and by varying this value of q, you can make a whole lot of distance functions, but these are for numeric values, right? But at times in our data set we can have binary we can have binary variables as well in the complete data. All variables of a record has either value true or false, true or false, true or false. So applying the Manhattan or Euclidean distance there will not be appropriate, right? So we will have to have distance function for a different distance function for such issues, right? Then but before going into the details of the specific distance function for binary variables, we need to know the difference between symmetric and asymmetric binary variables, right? For example, for example, we have a column, we have a column gender, right? And for a particular domain, for example in academics, if we have students in the class, right? So if the student is a male student or if a student is a female student, right? So it does not matter for us, right? Both will be treated equally, right? So it means that this gender column is a symmetric binary variable. Whatever the value of the variable is, either it's true or false, either it's 1 or 0, either it's on or off, it is symmetric. Both values will be treated as the same. But for example, if in a medical laboratory we have certain tests, for example test for sugar level, for example test for certain diseases, right? And the result is the outcome. And the outcome, of course there are certain values in each and every medical report, but at the end of the day the outcome is either positive or the outcome is negative, right? But here these positive and negative cannot be treated equally, right? They cannot be treated equally because the positive has very serious consequences and negative has different consequences, so we cannot treat them equally. So these type of binary variables are asymmetric binary variables, right? So so for the so you have known the difference between the symmetric binary variables and the asymmetric binary variables. The formula for the for computing the distance between the binary variables which are symmetric is this one, and formula for the asymmetric is this one, right? This is usually called the Jaccard coefficient, right? Now for this actually we have to compute this matrix where we have to count that how many variables of record j and record I have both values 1. So we will be computing that number here, and how many variables for record I has value on, and for the same variable j has value off, right? So that will be b, and then c and d. But I'm quite sure you may not be grasping it, so let us consider an example here. Now for the sake of convenience, instead of going back and forth, I have placed the formula and the matrix. This is the matrix and the formula is here. So what I've done, I've pasted it here for you, right? Or rather for myself as well, so that I cannot go, I should avoid going back and forth. And this is the data set which we have. For example, this is the patient or subject's name, Jack, Mary, Jim, and this is gender, male, female, male, fever, yes, yes, yes. So you can see that all the variables are binary variables. Let us convert this data into actual binary formation, and where we are not interested in the particular gender, we are interested in the results of the various tests, which is fever, cough, test 1, 2, 3, 4, right. So this is the formula, but let me go back, and if you see here, we have picked the formula for the asymmetric binary variables, but depending upon the domain and whatever domain experts suggest, you can go for the symmetric as well, right, or asymmetric as well. Okay, now what we are doing, we are finding the distance between Jack and Mary, right? So this is Jack, and okay, blue, this is Mary, right. Now this value is representing B, right, and if you see here B, for B the number of variables 1 2 3 4 5 6 variables, the number of variables for which Jack has value 1 and Mary has value 0. If you see here, Jack has value 1 and Mary has 0, no, 1 0 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 no. So there are no variables for which Jack has value 1 and Mary has value 0. So we have placed 0 here, right. So this is fine. Now then we are going to compute C. Now if you see here C, for this we are finding number of variables for which Jack has 0 and Mary has 1. Okay, 0 1 9, 0 1 no, 0 1 no, 0 1 no, 0 1 yes. We have one instance where Jack has 0 and Mary has 1 value, and so here this is 1. Sorry. Then we have to compute A, and you see A here. For A we are finding the variables for which Jack and Mary both have 1 value, right. You see here 1 1 1 हो गया, this is not 1 1, this is 1 1, 2 हो गया, or 2, right. So this is 2, right. Similarly we will compute B as well and C as well, right. So putting these values in the formula, we find the distance between Jack and Mary, and similarly we can find the distance between Jack and Jim and Mary, right. So this is the computation of the distance when the data which we have is of binary type. Then we can have nominal values. Nominal values, you can call them nominal values, you can call them categorical values, where see, in the binary type of variables we only have two categories: on, off, yes or no, right. This is on, this is on, and this is off, right. Either we call it on, off, or we call it yes, or we call it no, right. But in categorical values we can call it an extended form of binary variables, where instead of having only two states, we have more than two states, but they are determined, like for example in a sorry, in a numeric value we can have any number, right. But in categorical values we will be knowing that, okay, out of these 4 or 5 values, only one value will be placed in the variable. So if you see here, for example, in the case of colors, we have red, yellow, blue or green, or maybe purple color as well, but these are fixed categories. So these are nominal values. For such variables, we can compute the distance between two records, record I and J, using this formula, where P is the total number of states, total number of variables. In this particular case, this is 4, and M is the number of matches, right. That out of, for example, there is a record I, there is a record J, and for example, this is value of one variable, this is value of second variable, this is value of third variable, this is value of fourth variable, right? Now if you see here, out of these 4 variables, there are 2 matches, right? So this is how this is computed. This is method 1, and in method 2 what you can do is you can convert whole of your data into a large number of binary variables, and then you can simply go for this formula. Now how will be you doing that? For example, okay, let me try to show it to you. For example, we have record 1 and we have record 2, and for example we say eye color, and we say okay here, right, and we say that okay, in the colors we can have only red, we can have only blue, or we can have only green, right? So maybe this person has eye red. Okay, I should have used red color, this, but red eyes don't make any sense. Okay, let me okay, for this green eyes, yes, green eyes can be there, so let us make it green, right? Green eyes, and let's say okay, red hair bhi nahi hote, but okay, let us go for red hairs, right? The guy has colored his hair or her hair. And then this second person has okay, blue eyes, and let's say green hairs, right? Now how can we convert this into a binary type of the variable? We can say okay, R1 and R2, right? And then we can have eye red, eye blue, eye green, and here red, here blue, and here green, right? Sorry. Now since this person has green eyes, we will be turning it on, and this person has red hair, yeah, here red, right? This one. The rest of the variables will be getting value 0, and similarly we will do for this second record as well. So this is how this record is converted into a large number of binary variables, and then we can simply use this formula instead of this one. Then we have ordinal variables, and in ordinal variables the rank of the variable matters. For example, in a company, your entry level job may be in a corporate sector, in an IT company, your entry level job may be a software engineer. Then you may be promoted to senior software engineer. Then you may be promoted to line manager or manager, and then to the software architect, and so on and so forth. So here there the rank does matter. So for the ordinal variables, usually what is done, the ranks are basically converted into the range of 0 and 1 using this formula, right? Where this MF is the total number of ranks, and RIF is the value of the record for which we are converting, which is being converted between the range 0 and 1. Right, so these were the a few distance measures. There are a lot other as well, but these were the major ones which are being used, right? The major clustering approaches, rather I'll be continuing with the example. I will be giving you or teaching you a clustering algorithm in the next lecture. So I will be covering the types of the various clustering as well there. So I think this is sufficient for now. Thank you.